This section is called Learning from Light, and our goals are to learn what the three basic types of spectra are. How does light tell us what things are made of? How does light tell us the temperatures of planets and stars? And how does light tell us the speed of a different object? The three basic types of spectra are shown in this drawing. They're called emission line spectra, continuous spectrum, and absorption line spectrum. Anything that gives off light, whether it's reflected or emitted, will reveal a spectrum. That is, if it's detectable in some way. So we'll learn what those three types are very quickly. This is how to generate a continuous spectrum. Take an incandescent or regular light bulb or sunlight and send that white light through a prism, the prism just being a triangular piece of glass, and it breaks the light into its different colors. The colors, as you can see, are in a definite pattern: red, orange, yellow, green, blue, indigo, and then a violet, or some people would call it a purple. But it's a continuous smooth transition from one color to the other. So the graph that you see there of intensity and wavelength shows what a continuous spectrum would be like. An emission line spectrum, though, is a bit different. It might come as the result of one element or several elements that are burning or glowing very brightly. Send that energy through a prism, and what you get are colored lines at very specific wavelengths. Those are spikes along which you could actually measure the wavelength of those spikes and determine what the cloud of gas is burning. An absorption line spectrum is basically the opposite of an emission line spectrum, where you might have a hot light source over on the left, but there's a cloud of gas that is absorbing different elements, different atoms. And when that light goes through the prism, it reveals black stripes. Stripes where there should be a color, but that color, whatever wavelength it is, has been absorbed by the cloud of gas. So this is exactly what you see on page 113 at the top, those three different types of spectra. So how does light tell us what things are made of? Well, light, depending on the wavelength and the chemicals or the atoms that are in that light, might be able to show some sort of change or jump as the atoms are being ionized or energized in some way. That transition gives off a photon. That photon has a very specific energy, frequency, and wavelength. So in this example, these are the energy levels of hydrogen. Those jumps from one level to the other are happening at very specific wavelengths. Those are the fingerprints of hydrogen. These downward transitions produce a unique pattern of emission lines, and what you see at the bottom and then is an emission spectrum of hydrogen, where those colored lines, the purple, the blue, and the red way over to the right, being at a very specific wavelength, tell us that that is hydrogen. Because the atoms can absorb photons with the same energies, there might be an upward transition presenting a pattern of absorption lines at the same wavelengths. So again, if there's an absorption of hydrogen, what might be a continuous spectrum is has these stripes, again at very specific places along the continuous spectrum, again identifying that it's hydrogen. So every element has a specific fingerprint, as it's called, and these are three examples: helium, sodium, and neon. Notice that helium has very few bars, very few colors. Sodium has even less, but look at neon. It has a huge number of red and orange and somewhat yellow places, wavelengths, that neon gives off because the atoms get moved up and down to a point where they can emit photons at these various wavelengths. So neon would obviously be a gas, an element that we might want to put into a glass tube, run some electricity through, and have those photons come off as something we know as neon lights. The combination of different elements can still let us identify what the sources are. In this case, we have a spectrum which gives us several different elements in the strip. Helium, there's oxygen, and there's apparently neon in this particular substance. This is the spectrum of the sun, which is kind of interesting. It would be a continuous spectrum if you took all of these strips and laid them out into one long strip, but there are places where there are black spots. The stripes are evidence then of certain elements that may be absorbed by the sun, by the atmosphere of the sun, such that those are retained or absent, and that actually identifies then what the atmosphere of the sun is. Now, what about light and temperatures of planets and stars? Well, this is something that a lot of people get into in a lot more detail, but we're not. Page 117 talks about the two laws of thermal radiation. And this example at the bottom right of page 117 kind of tells the whole story. If you put some type of iron rod or poker, as they have here, into the fire, it's going to increase in temperature. And as it does so, it gets brighter. Well, that's the first law, the Stefan-Boltzmann law, where you have a relationship between the brightness of something and the temperature that it's reaching. The second law is called Wien's law. It says that the poker will change from red to white in color. So there's actually a color change demonstrating the change in temperature. In this case, it might be going from black to red to white. That would be a typical color transition for something like iron. So, nearly all large or dense objects emit thermal radiation. Stars, planets, even humans give off some thermal radiation. An object's thermal radiation spectrum depends on only one property, its temperature. So that can tell us a lot about things like stars. Stars are out there with many, many different temperatures. Well, that's represented by different colors. So it's kind of a one-to-one sort of comparison or equation that we can look at to determine the temperatures of stars. Look at the color. Here's one that kind of describes it in a little different way. Three different objects. Hotter objects obviously emit more light at all frequencies. That's one rule about the hotter something is. And hotter objects emit photons with a higher average energy. So as you can see here, the wavelengths of light along the bottom show, and along the side here, relative intensity per square meter of surface. The hotter something is, the more to the left its curve is. So a hot 15,000 K star has a curve off to the left, whereas our sun is sort of a midpoint star, and a smaller, or I should say a cooler star like a 3,000 K star is off to the right. So it's going to be emitting more infrared energy. And of course we, as humans, are much, much cooler in terms of these temperatures, only 310 kelvins. So we're in definitely a thermal range as far as heat energy is concerned. So if you're going to interpret the spectrum of a star, this is the kind of thing you might be looking at. You might see some smooth parts to the curve. Those are parts of the continuous spectrum. You might also see spikes like you see in the ultraviolet area, and you might also see dips as you see in the infrared. That's part of the absorption spectrum of that particular object. So any one object can have variations in continuous, absorption, and emission spectra. Here's the reflected sunlight. Obviously this object is giving off, or is reflecting light in a continuous way. There's some thermal radiation, meaning there's some warmth to whatever the object is. These are the signatures of absorption lines for carbon dioxide. Some ultraviolet light is being given off by the atmosphere of this object, and it turns out this is the spectrum of Mars. So even though Mars doesn't give off light directly, there are things about Mars that we can discover when we get its spectrum. And the last thing about light is that it can tell us the speed of a distant object. If a train, in this example here, if a train is stationary, we might have the engineer honk the horn, and of course, no matter where we are on the left or the right of the train, we hear the same pitch to the sound. If the train's moving to the right, as you see in part B of this picture, the sound waves are compressed. So the pitch of the horn will be higher. And of course, the person on the left of the train, the wavelengths are going to be a bit longer, so we're going to hear a lower pitch sound. Well, the same is true of light. If something is moving toward us in terms of light, the wavelengths are going to be compressed. In other words, shorter wavelengths or toward the blue end of the spectrum. That means that the object is moving toward us, and we call that the object, we say the object is blue shifting. The person on the left, however, has this light source moving off to the right, and the wavelengths are stretching out. Wavelengths are longer or moving toward the red end of the spectrum, so we say the object is red shifting. So it depends on where you are in reference to the object, whether it's red shifting or blue shifting. These are actual spectra of stars that might be used for comparison, and we might do in our activity on Tuesday, where the stationary spectrum of an object is at the top, and then we have several other spectra as examples of objects that are moving away or moving toward us. Object 1 is moving away from us because we can see the spectral lines are shifted toward the right or toward the red side. So that's red shifting. Whereas object 3 is moving toward us, and we can tell that because the lines are shifting toward the blue end of the spectrum. They're blue shifting. So the Doppler effect is actually able to tell us whether objects are moving away or toward us. But it doesn't give us all the information. Objects 1 and 3, we might be able to determine some type of Doppler shift. But object 2, even though it's moving, we don't have any Doppler shift there because it's not red shifting or blue shifting. It's basically maintaining the same speed in an upward direction in this case, but we don't get any red or blue shift. So there's no Doppler shift for object number 2. So what are the three basic types of spectra? There's the continuous, emission, and absorption. And how does light tell us what things are made of? Well, they have a unique fingerprint, and we can determine which atoms something is made of by looking at those fingerprints, looking at their spectrum. And how does light tell us the temperatures of planets and stars? Well, nearly all large or dense objects emit some sort of a spectrum that depends on temperature. And the spectrum of that radiation tells us the object's temperature. That's going to be very, very important when we study stars. Finally, how does light tell us the speed of a distant object? Well, the Doppler effect tells us how fast an object is moving toward us or away from us, depending on which way the spectrum is shifted. If it's shifted toward the blue end, we call that a blue shift, and by that we know the object is moving toward us. A red shift would mean the object is moving away from us.